Okay, so in the previous lecture, we were discussing about polynomial matrices, right? Yeah, our intention was to give sort of an algorithm to find out whether how to find the rational canonical form. And if you quickly recall, the rational canonical form of a matrix is simply uh, is a, is a is a block diagonal matrix where each block is a companion matrix of each of the t annihilators p1, p2 till pr corresponding to non-zero vectors alpha 1, alpha 2 till alpha r, which give the cyclic decomposition of the given finite dimensional vector space. And the T annihilators also have a special property that pk plus 1 divides pk, and p1 comes out to be the minimal polynomial of the given linear operator. Right. So these are the topics which we had covered previously. For the past, I guess, 5 to 6 lectures, we have constantly been discussing about cyclic decompositions and related topics. So quickly go and check those topics, then things will be clear. Okay. So in the previous lecture, we had introduced the concept of row operations on a polynomial matrix. And we had also discussed the fact that the concept of a row reduced echelon form doesn't arrive trivially for a polynomial matrix. Instead, what we try to do is that we allow both row and column operations together. Both are obviously analogous. Once we have defined the row operations, the column operations are obviously analogous. So we allow both row and column operations to a given matrix, and then we reach some matrix which is in simpler form. We obviously can't call this matrix as a row equivalent to this matrix we started with. We call it to be an equivalent matrix, to be precise. We have discussed these facts with the previous lecture. Let us start with a lemma. Okay, it is obviously in continuation with the previous lecture. The lemma says that let us consider a polynomial matrix. Okay, so let M be a M cross N polynomial matrix. Yeah. Uh, Such that M has some non-zero entry in its first column. Okay, such that M has some non-zero entry in its first column. Okay, in its first column. Yep. And we let's say P, or let's use a simple row, to be the greatest common divisor of the entries in column one. Okay. So we have some non-zero. So it for the GCD to exist, we require some non-zero entry, right? So M has some non-zero entry in its first column, and let row to be the GCD of the entries in the first column of it. Okay, in the first column of clear. Then M is let's call it to be row equivalent. Then M is row equivalent to a matrix N, and N carries a special form, that the first column of N, with the first column of N being of this form. So it's of the form row 0 and all the other elements are 0 as its first column. Clear? As its first column. Clear? Okay. So what are we actually doing is that we are sort of you know making all the elements of the first column 0 except the first element, and we are also kind of reducing the first element to the GCD of all the entries in the first column. Okay. So the proof of this statement completely lies in giving an algorithm to how to specifically do this thing. Uh, so precisely, it's a constructive proof, and let me give a give the proof to it. The proof is somewhat of this sort. So let us consider M to be the matrix, which is already given, by the lemma. So what we do is that we choose the first column. Let M1 be the first column of M. Be the first column of M. Okay. So M1 has some non-zero entry. Let us give a structure to M1. Let M1 be of this. So it's F1, F2, and so on. Till say so. The matrix has dimension M cross N, right? So there should be M elements. Right? Yeah. Okay. We define two important quantities. One is LM1, which is defined to be the minimum of the degrees of these polynomials Fi's. Okay. Obviously, for all Fi is non-zero. And then we define rho of M1 to be the GCD of these polynomials. So F1, F2 till Fn. Okay, so rho of M1 is what we are given as rho in the lemma. Yeah. Okay. Now we choose some index j such that this minimum degree is attained. Okay. Let j be some index such that degree of fj is this smallest degree. Okay. L of m1. Yeah. Now if I consider any arbitrary polynomial, therefore for some I, we can write fi to be of the form fj times gi plus ri. This trivially comes from the Euclidean division algorithm, where we have ri to be 0 and or the degree of ri is less than degree of fj. Right? This is trivial. Now we come up to the algorithm which we want to do. What we do is that for each I not equal to j, that is for each I different from j, we replace the ith row by the ith row minus gi times the jth row. What we do is, for all I not equal to j, we replace the ith row of m, to be precise, by ith row times, ith row minus gi times the jth row. Gi times the jth row. Why do we precisely do this? Because if you observe that the ith row contains this polynomial in the first column, jth row contains this polynomial in the first column, and fi minus fj, fi minus fj times gi is nothing but ri. Ri has this form, right? So we are kind of trying to reduce it down, right? So this will we have by ith row minus gi times the jth row, correct? Okay. Now what we do? Further reducing, what we do is we multiply the jth row, by the reciprocal of the leading coefficient of fj. So we multiply the jth row by the reciprocal of the leading coefficient of fj in order to make it a monic polynomial fj, and then interchange rho j and rho 1. So this polynomial is basically normalized to be a monic polynomial. This is having its leading coefficient to be 0, and we then send it to rho 1. Okay, we interchange it with row 1. So this polynomial goes to the first, to the 1 comma 1 position, correct? So this operation gives us a new first column. Now we are not concerned about any other column or row. We are just concerned about the first column. So this operation gives us the first column. Let us denote it as m1 dash. So the m1 dash is typically, so fj interchange with the first column after normalizing it. So let us write it as fj bar, fj tilde. And then in the second row, if you apply this algorithm, so you replace the second row by the second row minus g2 times the jth row. So you will get r2, right? So on and so forth till you reach rj minus 1, and then you start from 1 once again. So you have r1 till last you have rm. Clear? Let me emphasize this a bit more. So you have r1. Let me just write it down a bit. Okay. So you just go by the algorithm in this sense, right? So you have fj tilde, then you have r2, then you reach rj minus 1. Jth row is interchanged with fj. So fj would have the first row, right? Yeah, these two were interchanged, right? Correct. Is it clear? And then after r1, you have rj plus 1 because you are the jth row. So this is the jth row, right? This is rj. This was r1. Let me just emphasize this a bit. I guess it will be better to understand. Let me just frame this a bit in a more easier language. Okay. What happens to all the rows except the jth row and the first row? So we are not concerned about anything about the second row. We just choose an arbitrary index j. So suppose j is not equal to 2, 3, 4, and so on and so forth. J is a very specific index. So by the first statement, that is, we replace the ith row. So we replace fi, the polynomial fi, by fi minus gi times fj, and this is simply ri, right? So second row in the second row, the first column entry is r2, then you have r3, so on and so forth. You reach rj minus 1. That, so this is your j minus 1 row, right? J minus 1th row, let's say. Okay. The first row initially had r1, and the jth row initially had fj tilde after making its leading coefficient 1 by dividing the entire row by the leading coefficient of fj. But then what we do? We replace these two. We interchange these two. So after interchanging these two, the first, so fj tilde goes to the first row, right? And r1 comes up here. What is the next immediate entry? The j plus 1th row. In the case of the j plus 1th row, we should have, by this, we should have rj plus 1, right? And the rest of the pattern continues, right? So the last element you have r. I guess now it's clear. Okay. But okay. So to be specific, where fj is the monic polynomial, obtained by normalizing fj to have leading coefficient 1. To have leading coefficient. Clear? Now what can we say about a matrix which has m1 dash as the first column? So it is obviously row equivalent to m. We'll go to the next page. So evidently, since we have only used row operations, right? Evidently, m1 is m1. Okay, let me say, evidently, if m dash is the matrix with m1 dash as first column, then what are the observations we quickly have. The observations are basically that M dash is rho equivalent to M. So it's rho equivalent to M, right? One second, one second. Okay. So M dash is rho equivalent to M. Number two, what we have that the GCD of the elements in the first column of M dash is same as the GCD of the first column of M1. First column of M. This is pretty evident from the Euclidean division algorithm and the Euclidean algorithm to calculate GCD. There's nothing too different in it. You know that the GCD between the divisor and the dividend is carried to the GCD between the divisor and the remainder, right? So number three is that either the minimum degree of the polynomials in the first column of M dash, that is of M1 dash, is less than that of M1, or M1 dash is typically this is of this form. So it's row of M1 and all the other entries are 0, right? Now this is number three is pretty easy to observe from these two statements. You can do it on your own from this and this. Okay. Check this on your own. Evaluate this on your own. Okay. So this property actually is this property, to be precise, this is actually stating that either each, or I should say either some, or I should state it like this. Let me write it in this form that either there exists some I such that Ri is not equal to 0 and degree of Ri is less than degree of Fi, right? Or Ri is 0. Right? So that is precisely what I'm trying to speak out here. Correct? Okay. One second. Okay. Okay. Now the proof is quite simple. So this was an algorithm to calculate a matrix which has the first column of this form. I mean a first column of the form which we just discussed. But the lemma says that there is a matrix with the first column in the form of row and all the other elements also. That every the first column is of this form, to be precise. So how do we do this? Now what we do is that we now start with him. We start with it. We now start with the matrix M1, sorry, the matrix M, and obtain M dash. M dash is what we spoke just before writing the statement. Okay, now obtain M dash. Okay, if M dash is of this form, if M dash satisfies this form, that the first column is of this form, then we are done, right? Okay. If M dash satisfies the given lemma, sorry, I should say, if it satisfies the structure of n from given lemma, then we are done. Then we are done. Else, we apply the same set of statements to M dash. Okay. Else, apply the same set of statements to M dash to get say m dash whole dash, which we write it as m2. Okay. Again, if m2 satisfies the structure of n from the given lemma, then we are done. If m2 satisfies the structure of n from given lemma, then we are done. Right? Then we are done. Else, uh, we obtain m dash, m2 dash, which we write as m. Okay, and we continue the process, and we continue. Okay. The thing to observe is that at each step, L decreases. Right? Observe L of m1 was greater than is greater than L of m1 dash, which is greater than L of m1 of 2, and so on. And this process will obviously end, right, in not more than LM1 iterations. After not more than LM1 iterations, we have a matrix, say Mk, which serves as a from the lemma. Clear? Clear? Okay. I guess this statement is clear. This algorithm is very actually the important one. The algorithm we discussed before writing this proof was actually important. Okay. Now, as said in the previous lecture, we will only prove those statements which are important in calculating the algorithm to calculate the invariant factors. We are not gonna focus on the proofs of the other theorems, but we obviously gonna discuss them. So if we come to the next theorem, which is also quite analogous to what we had studied in the case of scalar matrices. It says that let P be a m cross n polynomial matrix. Let's say m cross m, a square polynomial matrix. Okay. Then the following are equivalent. What are the following statements? P is invertible. P is invertible. The determinant of P is a non-zero scalar polynomial. Is a non-zero scalar polynomial. In other words, an unit. Number 3, P is row equivalent. P is row equivalent to the m cross m identity matrix. And number 4 is that P is a product of elementary matrices. Elementary matrices. I'm not giving the proof of it, but let's leave it as an exercise. Obviously, try to use this lemma which we previously used to prove this theorem. Try to prove this theorem in this part. Okay, we prove 1 goes to 2, 2 goes to 3, 3 goes to 4, and 4 comes back. Okay, try it on it. Clear? What is an immediate corollary of this theorem? This is also quite analogous to what we had studied in the scalar matrices. The two matrices are row equivalent if there is an invertible matrix P such that suppose two matrices you have n and m. Let n, m, and n be polynomial m cross n matrices. Let's say. Then n is row equivalent to m if and only if there exists an invertible matrix P obviously in the same collection. This is a square matrix. This should be a square matrix. Sorry, this is a square matrix M cross M such that n is Pm. N equals to Pm. Clear? Now, obviously, the concept of elementary column operations are equivalent to concept of elementary row operations. So we are not introducing them, you know, separately. But since we were talking about introducing, or rather, I should say, using the row and column operations together for a matrix to reduce it down, so we define something which we call equivalence of matrices. Like we have row equivalence, we have column equivalence, and then we have something called equivalence. So if you start with a matrix and you apply a series of row operations to get some other matrix, then both of these matrices are row equivalent. Similarly, if you start with a matrix, you apply a series of column operations, you get another matrix, then these two matrices have to be column equivalent. If you start with a matrix and you apply a series of row and column operations together to reach another matrix, then these two matrices are typically said to be equivalent. Okay. So, definition, the matrix N is equivalent to the matrix M. M if we pass from M to N by a sequence of elementary row operations or column operations. Elementary row operations or elementary column operations. Okay. For example, you start with M, let this be M naught, you go to M1, you go to M2, and so on and so forth. You reach some MK and you get it to be. Okay. Each of them are either elementary row operations or elementary column operations. Clear? Okay. Now, in case of a row operation, we have this statement. In case of a column operation, we will have the matrix on the right hand side. So you can just simply come up with a theorem, which is also quite easy to prove. It says that if M and N are equivalent, so M and N are equivalent if and only if they are invertible matrices P and Q, such that N is equal to PMQ. Okay. So theorem, let M and N be matrices with polynomial entries, then M and N are equivalent, or we can say it as N is equivalent to M if and only if there exists invertible matrices P and Q, such that N can be written as PMQ. Obviously, observe that P is a M cross M matrix over the polynomial algebra, and Q is a N cross N matrix over the polynomial algebra. So we simply write it as, so P comes from this and Q comes from this, right? Clear? Let us come to the next immediate theorem. So yeah, let's do this theorem. I guess this is sort of important. Or let us just directly go to what we call the normal form definition. Let N be a matrix over the polynomial algebra again. We consider an M cross N matrix. We say that n is in Smith normal form, n is in Smith normal form if, or it's also often called normal form simply. If number one, every entry of the main diagonal is 0. Every entry of the main diagonal of n is 0. Okay. And number two, you have that on the main diagonal, what are the elements? So on the main diagonal, of n, there appear, obviously in order, polynomials f1, f2 till fl, such that fk divides fk plus 1. Okay, fk divides fk plus 1 for all 1 less than equals to k less than equals to l minus 1. Okay, what is this L? L is basically the minimum of the rows and columns, number of rows and columns, and the main diagonal entries are fk, right? So we can write it as fk, and we can also consider that to be nkk of the formula. That's not much problem. So this is the concept of a Smith normal form. Definition of a Smith normal form, to be precise. What is important is this following theorem. That is typically saying that every matrix over a polynomial algebra is equivalent to a Smith normal form. Let M be a matrix over the polynomial algebra. Then M is equivalent to a matrix N which is in Smith normal form, right? Which is in Smith normal form. Okay. And this matrix in Smith normal form is sort of unique. Clear? So obviously what we do is that we again give a constructive approach. We give an algorithm to calculate the Smith normal form. Now I should say this thing here. When you get the Smith normal form, when you have a matrix over the polynomial algebra, you find the matrix which is equivalent to, which is in Smith normal form. You have these polynomials f1, f2 till fl along the diagonal. Now these polynomials are only your invariant factors of f. So if you get the Smith normal form, you have got the invariant factors. Now if you get the invariant factors, according to their divisibility, you can judge the T annihilator. You can relate them with the T annihilators in case of the cyclic decomposition theorem. You find what the minimal polynomial is. Or rather, I can just say it in this form, that you can just arrange or visualize them in the form of the T annihilators you have in terms of divisibility. In case of the cyclic decomposition theorem, you simply consider the companion matrix of each of these polynomial, arrange them along the block in block diagonal form, and you get your rational canonical form. That's it, right? So let's give a proof to it. Proof. Suppose m is 0, we have nothing to prove, right? If m is 0, we have nothing to prove. We have nothing to prove. Else what we show? So let m be not 0. Now we show that, or we can consider an inductive approach. Okay. What I'm trying to say is that we show that M is equivalent to a matrix M dash such that M dash has the following form. So it's M1, all the other entries in the row and all the other entries in the column are 0, and this is M minus 1 cross N minus 1 matrix, uh, such that F1 divides every other entry of R. If you prove this, then we can work out the same thing for the matrix R. We get a polynomial F2, and we can continue so on and so forth, right? So it's sort of an inductive approach. So we just we it suffices to just show the existence of a polynomial F1 of this form. How do we do this? What we do is typically we follow the same approach we did in the lemma we proved. Okay. So let us go back to the lemma. Yeah, this was the lemma, right? So this algorithm which we have here, this complete algorithm, we we denote this algorithm to be A. Okay. So let LM be the, so we are going through the same approach. So it's minimum of the degrees of the polynomials of the non-zero polynomials uh, of the first column, or we can simply take it to be the whole of, okay, so degree of the maximum non-zero polynomials of, okay, because we still do not know, we do not have the hypothesis here that the first column consists of all non-zero entries, right? What we do is that we find the first column which contains an entry with the degree LM. Okay. We find the first column which contains an entry with degree L. Okay, clear? Then what we do? We interchange this with column 1. We interchange this column with column 1. Let the resultant matrix be M0. Okay. Obviously, we can apply the algorithm A for M0. Okay. So, what we can do is typically we describe an algorithm to find a matrix of the form, the matrix of this form, right? So you have G in the first entry and all the other elements are 0 here, all the other entries are 0 here. There is an arbitrary matrix. You're not concerned about this, which is equivalent to MC. Okay. How can we do this? We apply algorithm A to MC. We apply A to M0. Okay. Clear? So if I apply A to M0, then we get a matrix which has the first entry of the first column to be some matrix P, and all the other entries in the first column is 0, right? We get a matrix, say M1, such that M1 has this, right? So M1 has the form some polynomial P, all the other entries in the first column are 0, and the rows we are not concerned yet, right? And here we are. Clear? Okay. Now, if all the entries in the first row except P, that is all the elements from A to B are 0, then we are done, right? If the entries A to B are 0, we are done, right? Then we have already got the form which we wanted, right? We're not we have not yet discussed about the divisibility, but we have got the structure at least. Else apply the analogous algorithm of A, say B, for the first row. For the first row. Okay. To get the matrix, say M2. Now the elements in the first row except the 1 comma 1 entry are all become 0, right? So these elements become 0. The first entry now becomes some q, but the elements in the first column except q, they are again now non-zero. They can be 0, but they are manipulated as well due to this algorithm. So this becomes some a dash. Clear? Now what is q? Obviously by the lemma, q is the GCD of P and the elements A to B, right? Right? Now if we have not disturbed the elements of the first row except the element q, sorry, the first column except the element q, then we have nothing to do. Else again apply. If the first column is not disturbed, then we are done. Else apply A again, and the process continues. That is, on applying A, if we have disturbed the first row, then again apply B. If again applying B, we have disturbed the first column, again apply A, and so on and so forth. Apply A, and the process continues. Clear? Clear? So what we are typically doing is that we start with the matrix A, we apply A, we get M1, then we apply B, we get M2, we apply A, we get M3, then we again apply B, and it continues. But this process ends finitely, because at each step L, the value of L, it constantly decreases, right? After each successive step, L of mk plus 1 is less than L of mk, right? 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 Therefore, the process terminates finitely, and we get the desired structure, right? And we get the desired structure at some m, right? Right. So, suppose MT has the structure which we had previously discussed. Suppose MT has a structure of this form. So it's G0, all the elements are 0 here, you have 0, and here you have this matrix, right? Right. Now G may or may not divide every entry of this block. Suppose this block is S. Okay. Now G may or may not divide every entry of S. Okay. If it does not, okay, we find the first column which has an entry not divisible by G. We find the first column with an entry not divisible by G. Okay. What do? We add that column to column 1. Okay. And we add that column to column 1. Clear? So if the entry we have which is not divisible by G, then by the Euclidean algorithm, that entry can be done as sum in the form of G times H plus R. H is sort of the polynomial quotient, R is sort of the polynomial remainder. So column 1, therefore column 1 contains both G and an entry GH plus R with R non-zero, right? Because it does not divide. And then what is the other assumption property for R? That its degree is less than Q. So G, right? Right. Then we use the complete procedure which we had used to get the structure. So this procedure, we use this complete procedure which we had used to get this structure. Suppose this procedure is mentioned as C. We reapply C to the new matrix to get another matrix of the desired form with the degree of the corresponding G has decreased, okay, where the degree of the corresponding G has decreased, right? Obviously, it will again end up after a finite number of steps, right? And we will reach a matrix of the desired form. This procedure again terminates after a finite number of steps to give our desired matrix, right? Clear? So this is the complete algorithm. Okay. Now what do we specifically do? How is it related? Okay. Okay. So suppose we have an n cross n matrix. Let A be an n cross n matrix over a field F. Okay. And let P1, P2 till PR be its invariant factors. Be its invariant factors. Okay. Just the thing is that xi minus a, this matrix, then this comes out from the polynomial algebra, right? So it's from f in fx n plus n, right? And this has a normal form, right? So this has a normal form or a split normal form, which has the diagonal entries, which has the diagonal entries 1, 1, 1, and then we have PR, PR minus 1, and so on till P1. Clear? Got it? This is the procedure. Got it? Okay. Yeah. So we have discussed about the algorithm to calculate the invariant factors of a given matrix. In the next lecture, we will discuss again about Jordan form of matrices. It will be completely independent of the concepts of cyclic decomposition theorem. We will be discussing about the Jordan matrices from a independent matrix point of view, and then we will discuss another concept of the exponential of a matrix. Okay, so these will be the two topics which we'll be covering in the next few videos. So meet you guys in the next lecture.